Hey everyone, and welcome to today's Explainer. Today, we are absolutely unpacking the ultimate machine. We're going to completely deconstruct the architecture of high-performance computing. We'll be journeying all the way from the microscopic scale of a single tiny computer chip right up to those massive, warehouse-sized macro clusters that literally power our modern world. It's a world of just immense, mind-boggling power, and, well, we've got a lot of ground to cover, so let's jump right in.
But before we even touch the hardware, we have to start with one fundamental question. How do we build a computer fast enough to actually simulate reality? I mean, whether we're forecasting chaotic global weather patterns, modeling the incredibly complex folding of proteins, or rendering the hardcore physics of a brand new spaceship, standard processors just don't cut it. To push into the realm of exascale computing, or to build those massive AI supercomputers like Fugaku and Frontier, everyday computing logic completely breaks down. We need something purpose-built for the extreme.
Okay, so here's our roadmap for how we're going to build this out today. First, demystifying high-performance computing. Second, the heterogeneous engine. Third, sharing the load. Fourth, tying it together. And finally, orchestrating the giant.
Section 1. Demystifying high-performance computing.
To really grasp what we're looking at, we absolutely have to establish the difference between two computing paradigms that are, frankly, incredibly easy to confuse. High-throughput computing, or HPC, is essentially taking a bunch of everyday commodity PCs, the kind you might find sitting in any office, and using them to run independent farming jobs. They do their own thing without needing to constantly talk to each other. But high-performance computing, HPC, that's a completely different beast. It relies on dedicated hardware and, crucially, high-performance interconnections specifically designed for parallel computing. It's not just about having lots of processors, it's about how unbelievably fast they can whisper to one another.
Moving right along to Section 2, the heterogeneous engine, CPU plus GPU.
Now that we've separated the true specialized supercomputers from the standard commodity clusters, let's zoom in microscopically. Let's look at the very brain of our ultimate machine. Today, building a supercomputer means relying on a mix of processor types. Think of a CPU like a small, elite group of highly skilled, specialized workers. It features, say, 4 to 12 very powerful cores built for coarse task and data parallelism. They grab a single, long instruction thread and just run it as fast as mechanically possible. On the other hand, the GPU, the graphics processing unit, represents fine data parallelism. It is basically a massive factory floor with thousands of simpler workers. It uses SIMT, single instruction multiple data parallelism. It runs many concurrent threads much slower, but, and here's the kicker, it does them all at the exact same time.
This team-up happens in what we call a modern host accelerator model. The GPU multiprocessors actually interface directly with their own dedicated device memory, totally separate from the CPU's main memory. The CPU acts as the host, managing the main logic and the overall flow, while offloading all that incredibly repetitive, heavy-lifting math over to the massive parallel structure of the GPU accelerator.
And this brings us to a really, really important term for your vocabulary, GPGPU, or General Purpose Computing on GPUs. What started out years ago as hardware literally just for rendering video game graphics has become the absolute backbone of large clusters, as the entire industry pushed hard for more power-efficient chips, rather than just blindly cranking up clock speeds and melting everything down. Harnessing this high-throughput aggregate GPU performance for general science became completely non-negotiable.
Which brings us to Section 3, sharing the load, memory.
Okay, so we have our incredibly fast, specialized processors. But processors are utterly useless if they can't access the data they're supposed to be computing, right? The first approach to solving this is shared memory, and it's beautifully straightforward in concept. In this model, which is often programmed using OpenMP, all processors have immediate access to all the data. There's no explicit communication required from the programmer to move data from point A to point B. It utilizes lightweight threads to mutually access data with bindings ready to go for C, C++, and Fortran. Honestly, it's a lot like having a giant whiteboard in the middle of a room that every single worker can read from and write on at the exact same time.
Now contrast that approach with distributed memory. We see this architecture in heavy-hitting systems like the Cray XT4. Here, processors have their own private, localized memory. They can't see the giant whiteboard. If a processor needs data that lives in another processor's memory, well, the programmer has to explicitly write code to tell the system exactly how and when that data gets communicated. It is definitely more complex to program, but the payoff? It scales up far, far larger than a single shared whiteboard ever could.
But what if we could somehow get the best of both worlds? That is exactly where ccNUMA comes in. It stands for Cache-Coherent Non-Uniform Memory Access, and it's a completely fascinating bridge technology. What ccNUMA does is take memory that is physically distributed across different hardware, and it uses advanced network logic to trick the system. It basically makes all that physically separated memory appear to the software as one single massive shared address space. It's like an illusion, but a highly functional one.
In practice, modern supercomputing relies heavily on a hybrid architecture. You'll find local shared memory pools that are then linked together over a massive overarching network. It's distributed at the macro level, but fully shared at the micro level. This perfectly sets the stage for our next crucial topic, the physical networking layer that makes this hybrid dream a reality.
Section 4. Tying it together. Networks.
If the CPUs and GPUs are the brains of our ultimate machine, and the memory is the thought process, then the network is absolutely the nervous system. In the world of HPC, we refer to this as the interconnect. The interconnect is the critical wiring, the specialized network chips, and the communication software that joins all these computing components together. When you pack tens of thousands of processors into close physical proximity, the interconnect is literally everything. It will unilaterally determine whether your multi-million-dollar cluster flies through a simulation or completely chokes on a data bottleneck.
And different supercomputers weave their nodes together in incredibly creative ways. For instance, the Tianhe-1 supercomputer utilizes a proprietary, screaming fast network based on enhanced InfiniBand QDR. Conversely, systems like IBM's BlueGene/L or the classic Cray T3E utilize what's called a 3D Torus interconnect topology. In a 3D torus, every single computing node is physically wired directly to its 6 nearest neighbors. It creates this highly complex, three-dimensional mesh of data pathways that's just a marvel of engineering.
Section 5. Orchestrating the giant. Clusters.
For our final step in today's explainer, we're going to zoom all the way out. We've built the chips, we've shared the memory, and we've wired them together with a massive interconnect. Now we look at orchestrating the whole giant. Every massive centralized cluster has a boss, and that is the cluster head node. Now, the head node isn't really there to do the heavy scientific math. Instead, it handles all the administrative purposes, accounting management, and maintenance services. It's essentially the gateway, equipped with network interface cards that constantly route traffic between the highly secure internal cluster network and the public outside world.
So what does all this theory look like in the real world? Imagine computing nodes, essentially independent computing units with their own OS and memory, often called blade servers or sleds. They are packed incredibly densely into large 1U or 2U chassis racks. These chassis aggregate the nodes, providing a backplane so they can share electrical power and those absolutely massive liquid or air cooling systems. This dense, roaring stack of hardware is exactly what you see when you walk the floor of a major supercomputing facility.
But how do you actually use hundreds of physical racks? I mean, you definitely don't log into them one by one. Cluster organization relies on something called clustering middleware. This software sits on top of all those individual nodes and performs a pretty incredible magic trick. It creates a single system image concept. It allows a user to sit at a single terminal and treat a massive room of thousands of computers as one single cohesive computing unit. This centralized management model is exactly what powered legendary machines like the famous K computer, which topped the lists as the world's fastest supercomputer back in 2011.
And really, that brings us right to the bleeding edge of the industry today. Because as we build chips that pack more and more GPU cores into every single physical node, the pressure on that network interconnect skyrockets. So what new topologies are we going to need to invent tomorrow? Will modular supercomputing, or maybe even the integration of quantum computing devices, be the key to breaking our current bottlenecks? The balance between raw compute power and network speed is a delicate, unending race, and it's what's defining the exascale era and beyond. Thank you so much for joining me on this explainer. Keep learning, and I'll catch you next time.